Coach Hyde. Got some hot science going on for you. We're going to be doing a little reading today. Bill Bryson, page 144 to 147. We're going to start on page 144 at the first new paragraph page. So just bear with me to go through this as we're reading. Please follow along in your text. We're going to stop at some different signposts as we go through and discuss a little bit as we go. So, starting here, the upshot is that physics had two theories. Based on conflicting premises, they produced the same result. It was an impossible equation. We're starting out right here. We're kind of missing a little bit. I kind of skipped over a little of the meat for you. Just kind of get to the point here. We got two theories going in. So you kind of hear a little bit of talk of theories in here. Just know that so we're at that point in time in history. So here we go. Finally, in 1926, Heisenberg came up with a celebrated compromise, producing a new discipline that can be known as quantum mechanics. At the heart of it was Heisenberg's uncertainty principle, which stated the electron is a particle, but a particle that can be described in terms of a wave. So here we got a little signpost thing. First one is we're hearing this theory, and this is a modern theory, not the uncertainty anymore. Okay, moved away from that to this quantum mechanics. Quantum mechanics is a mathematical description of motion and the interactions of subatomic particles. So how things extremely small work. That's what quantum mechanics are. Whichever to, so when you hear quantum mechanics, that's what we're talking about. So let's get back to the book. Oh well, another thing, electrons. Okay, so here we see electron is a particle, but a particle that can be. So here on your screen, if you look, you check it out. We got a particle, but it's a particle that's described in a wave. So just kind of challenged my thinking, right? So what do we get? Some kind of particle wave hybrid? I don't even know what this image is, but it's on, I don't know, Google, maybe, right? So I was like, well, how can you be a particle and a wave? It had to be either or. So, all right, let's continue. The uncertainty around which the theory was built is that we can know the path of electron takes through space, or we can know where it is at a given instant. We cannot know both. Any attempt to measure one will unavoidably disturb the other. This isn't a matter of simply needing biasymmetry. It is an immutable property of the universe. Right, so check it out, right? Contrast, contradiction. So you see here, I got, can you please tell me the position and the path of travel of an electron? Nope, can't do it. That's what he's saying here. So that kind of stopped me, contrast, contradiction kind of thing. So we can usually predict these things with everything we know of. But now we can't. Not with these electron things right here, right? So let's see what's next. I forgot. Okay. So what this means in practice is that you can never predict where an electron will be at any given moment. You can only list its probability of being there. In a sense, as Dennis Overby has put it, an electron doesn't exist until it's observed. Or put slightly different, until it is observed, an electron must be regarded as being at everywhere and nowhere. So, just all the same probability, a little word gap here, signpost. So probability is the extent to which something is probable, likelihood of it happening. So you see Consolio, tell me the odds, here's somebody talking about the odds, just talking about probability. And then, sorry, coming in. Then we got this thing over here, the probability of them landing in the whatever, the tubes or whatnot. So how likely will something happen? What are the odds when we think about probability? So what about this being everywhere at once and being nowhere? So until it is observed, an electron must be regarded as being at once everywhere. So they're like everywhere, right? But then again, they're nowhere. What? What? Right? Right. It's okay. It's okay if that not makes sense. It don't make sense to me either. Right. Let's keep going. If this seems confusing, you may take some comfort in knowing that it was confusing to physicists too. Excuse me. Overby notes, Bohr once commented that a person who was outraged on first hearing about the quantum theory didn't understand what he was saying. Heisenberg when asked, "Hey man, how would one envision an atom?" Don't try. Just don't try. Don't even worry about it. It's not what happened. Just stop right now. Right? So that surprised me. You're asking one of these most famous scientists of the time, who's like credited with the discovery of the electron, all this kind of stuff. He doesn't start new principle. He's like, "Hey man, so tell me, how do I think I'll do it?" He's like, "Don't even worry about it." So here's a little gift here. All right. So I thought that was funny. I thought that was kind of funny to me. But so continue reading. Back to the book. So the atom turned out to be quite unlike like the image most people had created. They created in their head. That's what it's talking about. So the electron doesn't fly around the nucleus like a planet around its sun, but instead it takes a more amorphous aspect. So here we got, this is the planetary model. Okay, this is what it's talking about, that most people think of an atom, but no, this is just easier for our brains to understand. But it seems you already kind of knew about the planetary model. Um, And then an amorphous, this word you got, most people don't know what amorphous mean. It's without clearly defined shape or form. So here you got a picture of a diamond. If you look at the diamond over here, the blue, you see how it's really crystallized patterns. This is what crystallized means. Uh, Repeating patterns over and over, like a lattice fence. I don't know what that is. But then if you look at amorphous, it's very random. These are usually softer, more pliable, kind of like rubbers and stuff. So this diamond over here is definitely going to be worth more money than this one. Um, and it kind of gives you glares of the light. My diamond, I don't know what this stuff's called. It's just a rock to me, but you get the point, hopefully. All right, so back to the book. Uh-oh, my page slipped. The shell of an atom isn't some hard shiny casing as illustration of some type of current dust to suppose, but simply the outermost fuzzy clouds. Clouds itself is essentially just a zone of statistical probability marking the area beyond which the electron only very seldom stays. Thus, an atom, if you could see it, would look more like a very funny, fuzzy tennis ball than a hard-edged metallic sphere, but not much like either, or indeed like anything you've ever seen. We are, after all, dealing here with a world very different from the one we see around us. It seems as if there was no end. The first times is strange, simple, put it side by side account of the universe, our brains just aren't wired to understand. Or as Finland said, things on a small scale behave nothing like things on a large scale. So it's got spot right there, I think. Right. So this is kind of a little thing about scale. And scale is something that some of us have trouble with. Um, so this GIF here just kind of takes you from the macro scale down to the model. So we're talking about something from the quantum scale, which is, you know, really, really small, down here around the size of atoms and how they work. These laws of physics at this scale are very different than this massive celestial body um, world where you got planets and black holes and all that. So it's just very different. And then we kind of tend to focus in physical science in the world between these two with Newton's laws. So, which are very good laws, but they do definitely break down in the quantum level as well. So think about this scale. It's hard to imagine, and that's okay. Just kind of understand a little bit what's going on. Oops, too far. Back to the book. As physics delved deeper, they realized they had found a world where not only could electrons jump from one orbit to another without traveling across any intervening space, but matter could pop into existence from nothing at all. Providing the worlds of Al Lyman of MIT disappears and again with sufficient haste. So I'm like, time travel exists, right? Time travel exists. I just proved it. So it says jump from one orbit to another orbit without traveling across any intervening space. It's like a wormhole, but matter could pop into existence from nothing at all. It's crazy, right? Perhaps the most arresting of quantum improbabilities is the idea arising from Wolfgang Pauli's exclusion principle in 1925 that subatomic particles in certain pairs, even when separated by the most considerable distance, each instantly know what the other is doing. Particles have a quality known as spin, and according to quantum theory, the moment you determine the spin, of one particle, its sister particle, no matter how far away, how distant away, will immediately begin spinning in the opposite direction. But twins, right? Sister particles. So I think about twins. Supposedly know no matter how far apart they know exactly what they're thinking. So these particles, no matter how far apart they are, if you find the spin on one, the other one automatically starts spinning. It's crazy talk. Crazy talk. All right, back to the book. Find out where we are. It is as if. What is this? Oh, it's as if the world of science writer Lawrence Joseph. You had two identical pool balls, one in Ohio, another one in Fiji. The instant you sent one spinning, the other one would immediately spin in the contrary direction at precisely the speed. Remarkably, the phenomenon was proved in 1997 when physics at the University of Geneva sent photos 7 miles in the direction of photons and demonstrated that it interfered with provoking instantaneous response in the 7 miles away. It's pretty impressive. Things reached such a pitch that at one conference, Bohr remarked a new theory that the question was not whether it was crazy, but whether it was crazy enough. To illustrate the non-intuitive nature of the quantum world, Schrodinger offered a famous thought experiment in which a hypothetical cat was placed in a box. All right, so here we are. We got something to deal with. Hypothetical cat. All right, cat in the box. Gotcha. Was placed in a box with one atom of radioactive isotope attached to a vial of hydrocyanic acid. If the particle degraded within an hour, it would trigger a mechanism that would break the valve and poison the cat. If not, the cat would live. But we could not know which was the case, so there was no choice scientifically but to regard the cat as 100% alive and 100% dead at the same time. Never heard of this. This don't happen in Monticello. In Monticello, you can't be 100% alive and 100% dead. It's just it don't work like that here. All right, let's keep going. About to run out of time. I gotta keep this thing under 15 minutes. So I'm going to jump down to the next paragraph. Because of the oddities, many physicists dislike quantum theory, or at least certain aspects of it, and no more so than Einstein. This was more than a little ironic, since it was he and his Annus Mirabilis of 1905 who had so persuasively explained how photons sometimes behave like particles, sometimes like waves. Notion at the very heart of new physics, quantum theory is worthy of regard. He observed lately that he really didn't like it. God doesn't play dice, right? God doesn't take chance. Einstein couldn't bear the notion that God could create a universe in which some things were forever unknowable. Moreover, the idea of action at a distance, one particle influence another trillions of miles away, was a stark violation of the special theory of relativity. This was Einstein's theory. Yet here were physicists insisting that somehow, subatomic level information could. No one, incidentally, has ever explained how the particles. Scientists dealt with this problem, according to physicists, by not thinking about it. All of the above, there was a problem that quantum physics introduced a level of untidiness that had previously existed. Suddenly, you need two set laws to explain the matter of the universe: quantum theory for the world of the very small, and relativity for the large universe. So it's kind of like some. Oh wait, there you go. My bad, I got ahead of myself. All right, back to the reading. So the gravity of relativity theory was brilliant at explaining why planets or orbit suns, why galaxies tend to cluster, but it turns out to have no influence at all at the particle level. To explain what kept atoms together, other forces were needed. And in the 1930s, two were discovered: the strong nuclear force and the weak nuclear force. The strong nuclear force binds the atoms together, allows the portions of the bed, protons to bed down together in the nucleus so they don't repel and blow themselves apart. The weak force engages in more miscellaneous tasks, mostly to do with controlling the rates of certain sorts of radioactive decay. The weak nuclear force, despite its name, is 10 billion times stronger than the gravity. The strong nuclear force is more powerful, still vastly so, but their influence extends only the tiniest distance. The grip of the strong force reaches out only on about 1/100,000th of a diameter of an atom. So you're about to lose me. You got about half a page left to go. All right, before you go, I'm leave you with this number stack time post 10 billion billion. You get to see it right there. 1/1000th of a micrometer. And I'm out in 5. It's about to cut me off. Keep reading. Check it out. We'll talk about it in a minute.